In this video, I go and talk about the notion of a basis, and I show you a computational method to go compute a basis for the column space, the row space, and the null space of a matrix. So first, some motivation. What is it that we want? So if you recall, the vector form of a plane in R3, if it passes through the origin, is given by this formula. Notice that x is a linear combination of two vectors v1 and v2. Back then, I hinted what that does is it creates sort of like graph paper in this plane, so that if you give me any single vector in that plane, there's coordinates for it. So the inferred meaning is that every vector in that plane, x, has unique coordinates, and the coordinates are the coefficients in the linear combination that are relative, those coordinates are relative to the vectors v1 and v2. We want to know, can we generalize that for just all subspaces? Now you should notice two things about the way I've set up this particular vector form of a plane. First, it requires two vectors, and those two vectors are in different directions. They are therefore independent because they're not multiples of each other. But also, the equation itself says that every single vector in this plane can be formed as a linear combination of v1 and v2. So v1 and v2 spans the space of the plane. So what we want is to take those two ideas and to carry them forward. So as an example, for now on, we're going to say that a bunch of finite vectors, v1 through vk, is called a basis for a subspace if first the space is spanned by those vectors and those vectors are linearly independent. Now you need some kind of example of bases that you've already seen. So the standard vectors e1, e2 up to en form a basis for Rn. Also, from a previous video, a couple of videos ago, I showed you the vectors 1, 2 and the vector -1, 1 span all of R2. It took a while to do that. And I also showed later on in that same video that they were actually linearly independent. So those two vectors actually together form a basis for R2. They make a grid, a coordinate grids on top of R2. It's just not the one that you're used to. For now, let's just ignore discussing the properties of a basis. And also the question of whether a subspace even has a basis, because the definition just states that if a set of vectors has these two properties for a subspace, then it's called a basis for that subspace. That's not the same as saying every subspace has a basis. Again, that question, later on. We have a serious computational problem, which is how do we even find one? If we know a certain subspace has a basis, how can we go about finding it? So let's focus in on the just three, of the fundamental subspaces associated with a matrix. That would be the column space, the row space, and the null space. I'm ignoring something like the row space of A transpose, as that's just the column space of A. And I'm also ignoring like the null space of A transpose, because if you know how to find the basis for a null space of any matrix, it doesn't matter if the matrix was the original matrix or its transpose. To go further, you can also note that the column space of a matrix is just the span of its column vectors. So you can reverse that. If I show you how to find a basis for a column space, you can always then, if you give me this any kind of spanning set, you can take those vectors that create the spanning set, think of them as column vectors, make a matrix with those columns, and then a basis for the spanning set of those vectors is just a basis of the column space of the corresponding matrix. So by using these properties, these examples, you can find a basis for any spanning set. It winds up being that when you argue what's the null space of a matrix or row space of a matrix or a column space of a matrix and how to find its basis, the argument's always the same. It's a different argument for each of the cases, but it's always the same. Because of that, it's really a lot easier to understand why this works if I just give you a numerical example and you just follow along the argument. It's very interesting, though, that in all cases, in order to find a basis for any of these spaces, what you always do is just go and find the reduced row echelon form. From there, you can get all the answers quickly. If you want, in the case of row space of a matrix and the column space of a matrix, you only actually need any row echelon form. You don't have to go all the way down to reduced row. And I'll show you why. So as an example, let's go ahead and find a basis for this row space. So then here is its reduced row echelon form. And I remember then that if one can be row reduced to the other, that means a row equivalent. If A and R are row equivalent, then from a previous theorem that we've done, that means the row space of the matrix A is equal to the row space of the matrix R. But the row space of the matrix R is the span of its rows. That's just by definition. But one of those rows is the 0 vector. And again, from a previous result, if you have a span of a bunch of vectors and one of those vectors is a 0 vector, you can just throw it out and it won't change the span at all. So that means then that the row space of A is spanned by the two non-zero rows in its reduced row echelon form. But then look at those two rows. When you look at those two rows, notice that they have leading entries in them, and all the other entries above and below those leading entries are 0. Because of that, that means then that none of the rows can be linear combinations of the rows preceding them. From a theorem I've already shown you, if that's true, that means that those vectors have to be linearly independent. Because if you remember, vectors are dependent if and only if one vector is a linear combination. And I said back then, and also you can say before them, of one of the vectors before them. It's really nice. So then these two vectors, these two non-zero vectors that form the non-zero rows of R, those vectors are automatically span the row space of A, and that they actually are also independent. With those two things, we can then say what the basis for the row space is. So the basis for the row space of this matrix is literally just the non-zero rows in the reduced row echelon form. And that's actually always true. The argument never ever changes. Also, you should notice though that the basis for this row space doesn't actually use the rows of the original matrix. That's in some ways unfortunate, because you'd like to sometimes keep the original rows, and this technique doesn't do that. The next simplest to understand, because you have a lot of experience with it, is how to find the basis for a null space of a matrix. So a null space of a matrix is just the set of all the solutions of AX equals 0. So let's just look at that corresponding augmented matrix for that system. We'll then just find its reduced row echelon form, like that. And then take this and write down the solutions. So then, if this is written in terms of a linear system, with the unknowns being x1, x2, so on, you could then write down the variables and instantly declare what the free variables have to be, which would have to be a, b, and c, since the leading variables in the equations are x sub 1 and x sub 3. You could then solve x sub 1 and x sub 3 in terms of these free variables. You could then write that in vector form by just ripping it apart like we've done before. You then have the vector x can be written this way. Notice that what you get is 3 vectors. And every single vector x that's in the null space is a linear combination of these 3 vectors. So these 3 vectors instantly span the null space. So that's really nice. But also though, those 3 vectors have got to be linearly independent, because if this vector x was actually the 0 vector, then since you have these leading ones, see them leading ones? Since you have these ones in these vectors, that would force that A would have to be 0, B would have to be 0, and C would have to be 0. Because x sub 2 would have to be 0, x sub 4 would be 0, and x sub 5 would be 0. So that means instantly these 3 vectors not only span the null space, but they're also linearly independent. That's great. So that means we have a basis. It's just these 3 vectors. But this is one of those times where it might be faster to not look at the whole augmented matrix. Notice that you don't actually need that last column. Get rid of it. Just get rid of the last column. Go from A and find its reduced row echelon form. Now what I want you to do is put little blocks over the columns that have the leading entries. So that was the first and third column. Notice that the remaining numbers here in the first row, see how they're here? And how that corresponds to the first row. That was the first block I wiped out. The next row of numbers in R, see how that's in the third row? And then, since I've run out of blocks that I wiped out in R, notice that the remaining rows in these vectors, they form the identity matrix. See it? They form the identity matrix. So that's actually a fast way. I'll be doing that a lot more. That's a fast way to write down the actual work to find out the basis vectors. You don't actually need the entire system. You don't have to solve it, in fact, at all. You can do this little trick to find out the vectors that span the null space and are linearly independent. So a basis for the null space of this particular matrix is these three vectors. It's just the vectors that form the solution to ax equals 0. If you want to do it the long way by writing it all out with the variables and then ripping it apart and then seeing the vectors, totally fine. If you want to do the trick I just showed you by kind of wiping out columns and noticing where all the remaining numbers have to go, that's also fine. Let's find a basis for the column space of that matrix. So to do this, I'm going to use a little trick. I want to first look at all the solutions of A times C equals 0. So that system corresponds to, when you row reduce it, to the system R times C equals 0. I'm just writing it in matrix multiplication form. What this means then that any linear combination of the columns of A that adds up to 0, you can use the exact same coefficients to form a linear combination of the columns of R to also add 0, because they have the same solution sets. So the entries C1, C2 have to be the same in both cases. But that means that column independence or dependence in A completely corresponds to column linear independence or dependence in columns of R, because the dependencies are exactly the same. So that means that if column 2 and 3 are linearly independent in R, then column 2 and 3 in matrix A are also linearly independent. If the columns 1, 2, and 3 in R are dependent, then the columns 1, 2, 3 in A are dependent. We're going to use that now. I want you to focus in on those columns. Notice the first and the third column in R are obviously linearly independent, because those guys are I and J actually in 3 space. They're E1 and E2, so they're instantly independent. But that would then mean then, since 1 and 3, the first and the third column of R, are linearly independent, that means the first and the third columns in A are also linearly independent. Look at the second column of R. Now the second column of R is 3 times the first. But that means that R1 and R2 are linearly dependent. That means A1 and A2 are linearly dependent. And in fact, you have the same coefficients. That means that A2 has got to be linearly dependent upon A1. Since R4, the fourth column of R, is equal to 1 times R1 plus 1 times R3, that means R4 linearly depends upon R1 and R3. But then, because of the comment I made, that means the fourth column of A also is linearly dependent on the first column and the third column of A. Lastly, the fifth column of R is linearly dependent upon the first and the third columns of R. But then, once again, that means then that the fifth column of A is linearly dependent upon the first and third columns of A, because we have the exact same dependence on both sides, because we have the same solution sets on both sides. But then that means then, notice or recall that the column space of A is just the span of its columns. But from a previous statement, if a vector is ever linearly dependent upon the others, you can remove it and it will not change the span. So A2, A4, and A5, those are all linearly dependent on A1 and A3. So you can take A2, A4, and A5 out of the set of vectors and it will not change the span. So that means then the column space of A is actually spanned by column 1 and column 3. And we know column 1 and column 3, they are linearly independent. So A1 and A2, A1 and A3, those, the first and the third column of A, they actually form a basis for the column space of A. This argument is always true. Notice the connection, that it's the first and third columns of R that have the leading entries, and it's the first and third column of A that are the basis for the column space of A. So we don't actually need all that work. The only thing we actually need is you take A, we row reduce it to get a reduced row echelon form, and we find out where the leading entries are. In this case, the leading entries are the first and the third column of R. So the first and third column of A, that's the basis for the column space, because they will be linearly independent, and they will still span the space. So a basis for that column space of that matrix is the two vectors, which is the first and third column of A. Because if you row reduce the matrix to its reduced row echelon form, its leading entries are in the first and third column. Notice that this process actually does use the original column vectors in the basis for the column space of A. It's really nice. You actually still use the original vectors. That's really convenient in a couple computational problems we'll see later on. Also, in this process, you don't actually need the reduced row echelon form, because once you have a row echelon form, the leading entries won't change. They won't change their position. So if you just get to a row echelon form, you can still find a basis for the column space by doing the exact same process. You don't have to go that far. The same is true, by the way, for the row space. All you have to do is get to a row echelon form and then just take the non-zero rows. That will be a basis. But for the null space, you actually have to go all the way down. You have to go drill all the way down to a reduced row echelon form in order to get the answer. Okay, let's just do one more example. Here's the matrix A. So what I would do is I would just go ahead and find its reduced row echelon form, as I'll need that at least for the null space. And then from here, it's easy to pick off then what is the basis for the column space. Notice the first and the second column of R correspond to where the leading entries are. So the first and second columns of A form a basis for the column space. Easy. And then also just as easy, notice that the basis of the row space of that matrix is just the non-zero rows in the reduced row echelon form. So that's those two vectors there form a basis for the row space of the matrix A. Now it's we're just talking vectors here. As it's just vectors, how you report them doesn't really matter. So you can write them either as row vectors or as column vectors. They're both fine, really both fine. Just make sure you stay in context based upon your particular problem. The last one would then be, what's the basis for the null space? Okay, so then look at the reduced row echelon form, wipe out the columns that have your leading entries, and then mark down the column they're in. So that's the two columns are the first and seconds. Notice then that means that the other rows, that's the third and the fourth, they have the identity matrix. So I write down two vectors, one for each leading variable, one for each free variable I would have had, and then I put down the identity matrix inside of it. And then these entries, if you take their opposites, they go in the first row and in the second row, because that's the columns I wiped out in R. First column, second column. So the first column, that means the first row is -2, -3, and the second column, that means the second row, I put down 0, 1. And that's it. That's a basis for that space. Nice, right? These techniques then will give you quickly will give you a basis for the column space, the row space, and the null space. All you have to do is figure out how to go and interpret the work. Notice that to do all this work, all you need then is the reduced row echelon form of the matrix. And that's unique, so you're always pretty much guaranteed. You're always guaranteed to find a basis for those spaces using these particular techniques. The question never is there a basis for these ones? There always is, because these techniques will always work. And I think it's enough. That's enough for this particular video. You should now know what a basis is, and at least be able to find a basis for the column space, the row space, and the null space of a given matrix.